In today's video, I will be going over lesson 5.5 on compound interest. So before we start talking about this, we need to understand what compound interest is. So compound interest is what happens with things like bank accounts or loans or credit card payments. So typically we think about it with a bank account. If I open up a bank account and put money into savings, we call that a principal, or the amount that I'm putting in. It's going to earn interest at a certain rate per year. And we can see in some of our examples, one, it's going to say like 6%. And so what's going to happen is every so often the bank is going to look at how much is in my account, and they're going to give me 6% of that amount if that's the rate that they're charging. Okay, and so the amount that is in my account is going to start to grow. And each time they look at that, they're going to include that the interest that they already paid. So let's say that I had $1,000 in there. After interest at some rate, now I'm at $1,010. Okay, so the next time they go to apply my interest, I have $1,010 in there. So I would get even a little extra interest because it's compounding on the interest that's already in there. So that's kind of what compounding means, is it's building upon what's already there, and it can build upon itself. So, by the end of today, you should be able to solve problems involving compound interest. And if interest still doesn't quite make sense to you, that's okay. Okay, we're just going to look at the formula and how you would plug things into it. So, compound interest, by definition here, says it's the interest earned on the principal, meaning the amount in your account, and on the previously earned interest. And if we look over here to the right in this box, up in that little cloud, it shows our formula. It says y equals p, and in parentheses 1 plus r over n to the nt power. And we're going to talk about what that means. But before we do you see how this looks pretty familiar to our exponential growth formula from last time? We have some value times 1 plus our rate to the t. There's just a few more pieces added in. So they're very similar. We can see that the a value was switched out for the p. Okay, it's still basically the same thing. This is the initial amount, or the principal in our account. They just are using a p because principal is the word we use when we're talking about money in an account. Okay, the 1 plus our rate part, that's the same, but now they're dividing it by n. N is the number of times the interest is compounded per year. So what can happen is when the bank goes in to compound the interest, they could do it once a year, in which case your n value would equal 1. They can do it semi-annually, and semi-annually means twice a year. They could do it quarterly, which is 4 times a year, or they could do it monthly, which is 12 times a year. So that's what's going to determine your n value. And what's happening is they're taking the rate for the whole year and just dividing it out or between however many times they're going to apply it. So if they're going to do it 4 times, they take the total for the year and divide that by 4. Okay, then they put the n up here as well, n times the t, because if they're doing it 4 times in the year for 3 years, okay, you'd have to do 4 times 3. They're going to compound it 12 different times. So this tells us the total times that it's compounded. So if you don't quite understand why all those pieces work, that's okay. We'll get there. But what you do need to understand is where each of these pieces comes from and how we plug it in. So this is the formula every time. This is your starting amount, your rate, which would be the percentage, and then we convert it back to a decimal, divided by how many times it compounded during the year, and that same number goes here, times the number of years. So we'll practice those here on these problems, so you'll get to kind of see this in action. So it's saying you deposit $1,000 into a savings account. We'll worry about what that is in a second. Okay, that account earns 6% annual interest that's compounded annually. They would like you to write a function that represents the balance after t years, then find the balance of the account after 10 years. If no withdrawals or deposits are made. So meaning if we don't change anything to our account, what would happen? And that will be true for all of these. So the pieces that I put a box around are the parts that we care about here. We know we started at $1,000. Our rate is 6%. It's compounding annually, meaning once a year. And we want to know the value at 10 years. So first we need to start by setting up our equation. And we always start with the y equals. I'm just following this formula right here. Y equals P. P is a number. It's the principal or the initial amount. If we look, we started with $1,000 in our account. So we're going to write that first. Then we're going to do 1 plus. That's always part of our formula. Okay, and then our rate. Our rate was 6%. As a decimal, that's going to be 0.06, or like 6 cents. Okay, if you can't remember how to do that, just do 6 divided by 100 on your calculator, and that would give you the same thing. Okay, it's compounding annually, so that's going to be our n value right here. The number of times per year, since it's just annually, our n value equals 1. It happens once, so we're going to do 0.6 over 1. And we put that 1 up there again because we use our n twice, times our t value. And that would give us our function. They want to know what happens after, or how much money is in the account after 10 years. So now we're just going to plug in 10 for t. So we have our 1,000, 1 plus 0.06 over 1, okay, which would really just be 0.06. And then 1 times t, or 1 times 10, which gives us 10 up here. Type that into our calculator. We're going to go 1,000 times 1 plus 0.06 divided by 1. It doesn't change, so I'm just going to write it like that, to the 10th power, which equals $1,790, and we'll round it to the nearest cent. So it was 85 cents. Same idea on all of these. You deposit $1,600 into the bank. Okay, we know that that's our starting amount. It goes first, $1,600, or $1,600. So you deposit that into a bank account that pays 1.8%. So we're going to do 1 plus, set up our fraction, it's doing 1.8, so that's going to be 0.018. We convert that to a decimal. Annual interest, and it's compounded quarterly. So that means it's going to compound 4 times during the year. So our n value is going to be 4. So right here we put a 4 under our fraction and 4t up here. 4 for our n value, and t is just our variable that we plug in. So they would like you to find the balance after 3 years. So we can type this into our calculator. We're going to go 1,600 times 1 plus, set up our fraction, 0.018 for our 1.8%, 4 times a year for 4 years, or sorry, not for 4 years, 4 times a year for 3 years. They said that right there at the very end. So we're going to do 4 times 3. And that gives us a total of $1,688.57. So after the 3 years at 1.8%, their account earned $88.57 in interest. Up here they earned $790.85 in interest. Okay, so the money in your account can grow just by sitting there. On number 3, the first credit card that you got charges 12.6% interest, so that's our rate. It compounds that interest monthly, so we want to know that it compounds it monthly. So that's an n value of 12. Within 1 day of getting your first credit card, you max out the credit limit by spending $1,200. If you do not buy anything else on the card and you do not make any payments, how much money would you owe the company after 1 year? So this is something that happens to people all the time. They'll get a credit card, they'll reach the credit limit on it, and then they're left owing lots of money. And the credit card companies, they like to charge interest, making you pay extra for using their money. So let's figure out how much you would owe after 1 year. And this is if you just let it sit. how much extra they're going to charge you. So you started at $1,200. 1 plus is part of our formula. Okay, our rate, 12.6% as a decimal, that's going to be 0.126, or 0.126. And it's compounding every month, so 12 times a year. So we're going to put the 12 up here, times t, so it'll be 12t. And then we want to find what that equals after 1 year, so we'll use 1 for our t value. Everything else will get plugged into our calculator. We're going to do 1200 times 1 plus, with our fraction, 0.126 over 12 for each month. Raise that to the 12 times 1, or just to the 12th power. So, even though you only spent $1,200, they're going to charge you an extra $160.24 just for using their credit card. That's what that would equal after the interest compounded for a year. Okay, on this last one, you deposit $500 into an account, so that's our starting value, that earns 9% annual interest, compounded monthly. So compounding monthly, that's happening 12 times in the year. So n equals 12. They want you to write a function that represents the balance after t years. Use the function to find the balance after 5 years. So we start with a y equals, we started with $500. 1 plus is part of our formula. Our rate is 9%, so we've got to write that like we would write 9 cents, or 0.09. Compounding monthly, that's 12 times in the year, and we'll put 12t up on top. We want to know what this would equal after 5 years. So we're going to plug in 5 for t when we do this on our calculator. So we have our 500 times 1 plus our fraction, 0.126 over 12. We're raising that to the 12 for our months times 5 for our years. Okay, 12. So that's our n and our t value. So that gives us, I think I typed it, oh, I did the wrong, I was like, that doesn't look quite right. I used the wrong interest rate. We're doing 9%, sorry, instead of 12.6. I was still thinking of the last one. 0.09, you guys are probably looking at that saying, where did she get that from? So that would be $782.84. So 1 plus our rate, which was the 9%, I'm sorry, I typed in the wrong one, compounded monthly for 12 months for 5 years, so we get 782. Okay, go ahead and turn the page. So that's all there is for compound interest. It's the same idea as exponential growth. We just have to add in those n values because they compound it more than once a year most of the time. Sometimes it's just once. On the back here, they're just reviewing some of the things that we talked about last time, reviewing exponential growth and decay. So on these ones, and the numbers are all funny on them, they just want you to decide if it's exponential growth, exponential decay, or neither. So exponential growth will be going up by a multiplying pattern, decay would be going down by a dividing pattern, and if it's arithmetic, it's not going to be either of these. So looking at these first ones, we're checking out the y values here. We can see that this is multiplying, getting bigger, and it looks like it's multiplying by 3 each time, so this would be exponential growth. This one we can see it's going down by half each time, so this would be exponential decay. And then over here we can see that it's adding 5 each time, so that would be linear and not exponential. So that would have to be neither. So even though it's growing, it's not growing exponentially. Okay, 6 through 11 down here, again the numbers are kind of funny on these. They would like you to determine whether the function again represents exponential growth or exponential decay and identify the rate of change as a percent. So remember, if it's decaying, the value will be less than 1. If it's growing, it'll be more than 1. And the value we're talking about is the one being raised to the t, or to our exponent. So inside our parentheses here, 0.4 is less than 1, so this is going to be decaying. And the amount that it's decaying by, remember, In our formula, we do 1 minus the rate. Okay, so they did 1 minus some number and we're left with 0.4. So 0.4 is 40%. So if you have 40% left over, that means the amount it decreased by was 60%. On number 7, our rate is greater than 1, so we can see that this is representing growth. And our formula told us to do 1 plus our rate. This is just part of the formula, not the whole thing. So the part being added to 1 is the 0.3, and 0.3 as a percent is 30%, so it's going up by 30% each time. On number 8, it's greater than 1, so this is going to show growth, and the amount extra from the 1 is the 0.07, or 7%. Number 9 is less than 1, so that's going to show decay. And what this says is that after each year or sequence or whatever, there's going to be 25% remaining, which means it went down by 75%. Okay, the missing piece there. And you can figure that out by doing 1 minus this amount on your calculator, and it'll tell you what's left over. On number 10, this is showing growth because it's greater than 1 inside of here, 1.36, and the 0.36 is the part that's been added to the 1, which is 36%. And on number 11 here, 0.8, that's smaller than 1, so we are decaying. Okay, and 80% will be remaining each time, which means each time it's going down by 20%. Okay, that was it for our notes. After this lesson, you should know how to do all of your topics, so go ahead and get those finished. If you're stuck on any of these or need more help or explanation with the formulas or growth and decay, come and talk to me. I'm happy to help answer your questions. Have a good day.